Welcome to College Algebra. In this lecture video, we're going to begin to talk about 4.5, the rational functions and inequalities. We've been talking a lot of rational functions before, so in this particular section, we're going to formally introduce them. We sing a lot of rational functions in chapter 3, okay? So this is where we've officially kind of put more label on some of the things that we saw before. The first thing I want to mention to you is something called the vertical asymptotes. So before that, let's take a look at what a rational function really is. What's considered as a rational function by definition is really like a fraction function where the numerator and the denominators are polynomial. Before, I remember mentioning to be a rational function, you got to have a variable x, or any type of variable in the denominator, okay? And that is still true. But by a formal definition, rational function is where numerator and denominators are made out of polynomials. All right. So what is so-called a vertical asymptote? A vertical asymptote is referring to a vertical line or vertical lines that will divide my rational function or my graph of a rational function into different parts. So in a minute we will begin, I will graph it to you and begin to show you what they are. Alright, quick note here, mentioned this before. Remember now, denominator of a rational function cannot be 0 because that will actually make the entire function undefined. Here, well, what we used to call it is called the restrictions on the domain. Back in chapter 3, we call them restriction on the domain, okay, where the denominator cannot be 0. So let's take a look at that, because that restriction on the domain actually has two parts to it, okay. One of them is your vertical asymptote, all right. Another part is actually the actual, both of them are restriction on the domain, but one of them is specifically is actually called the vertical asymptote. Alright, let me show you with a couple of examples here just in a minute. Alright, so how do I normally find vertical asymptote? First step, you got to factor the polynomial on the top and the bottom. Alright, reduce the factor if you can. Alright, so if I reduce a top and the bottom, whatever is canceled out, that would not be my vertical asymptote. So whatever I reduced, canceled out, okay, that factor set equal to 0 will actually be another restriction on the domain, but it's not going to be a vertical asymptote. So after reducing whatever is left over in the denominator, we will set those factors equal to 0 and solve for the variable. And those will be my vertical asymptotes. So for example, this numerator here is only one term, cannot be factored. Denominator already factored for me, so I don't have to do step number 1. Alright, there is nothing to reduce top and bottom, so step number 3, set each factor equal to 0 in the denominator, and I quickly see my x is equal to 5 and the other x is equal to negative 4. So when we're talking about the restriction on the domain, okay, x cannot be 5, x cannot be negative 4, because these two is called the vertical asymptotes. Alright, so the equation for the vertical asymptote is a vertical line, so that's x equal to 5 and x equal to negative 4. So let me graph this for you, because vertical asymptote sometimes does not show up on the graphing calculator. So if I will put 3x to the second power in the parenthesis divided by, I'm going to double up my parenthesis here for the denominator. So I open one to indicating the whole denominator is one term. I will open up another one for my x minus 5. Close it. Open one for x plus 4. Close it. Then close the whole denominator. And let me show you real quick the things you do not see. Alright, the graph of my rational function is actually bounded within a certain behavior, and those behavior are your asymptotes. Okay. Plus, you know, we also mentioned something about transformation. It make our graph behave nicely. So the part you don't see, okay, on this calculator is your vertical asymptote. X equal to 5, x equal to -4. 1, 2, 3, 4. So if I count right here, there's actually a vertical line here. 1, 2, 3, 4, 5. There's a vertical line right here. Okay, those are my vertical asymptote. That does not show up on the graphing calculator. Okay, so the equation for my vertical asymptote, one of them is x equal to -4. The other one is equal to 5. So again, they are restriction on the domain, but specifically, okay, they are called the vertical asymptote. Okay, so when we're talking about domain and range, coming from left, excuse me, we're just talking about domain for right now, coming from left, from -infinity approaching to -4, but you cannot be -4, because what's your -4 here? That is what? Vertical asymptote. So the reason why I'm using parenthesis here, because that -4 is a vertical asymptote. Union, my function also existed from -4 to 5, you know, in between those two vertical asymptotes. So these two numbers are still vertical asymptotes. Union, pick off on the right hand side of the vertical asymptote from 5, keep on going to infinity. Alright, so a broader terminology will be restriction on the domain, okay, to be more precise. Some of these restrictions are called the vertical asymptotes. Alright, let's try another one, okay? Alright, factor, and then we're going to reduce. X plus 7, there's nothing to factor, but I'm going to put them in the parentheses to indicating that I already factor out a 1. Alright, denominator x squared minus 49 is a difference of squares, so that will be x plus 7 times x minus 7. And this is a very interesting example, because if I will reduce my numerator and denominator, the plus 7 cancels out. So that leaves me with x over 1, excuse me, they leave me with 1 over x minus 7. So I set my denominator equal to 0. So the next step, set each factor denominator equal to 0, solve for the variable. So my vertical asymptote will be x equal to 7. So the 1 I canceled out is not going to be a vertical asymptote. It's whatever is after the canceling. Those factors in the denominator set equal to 0 become vertical asymptote. I'm going to graph this problem for you though. Very interesting little problem. X plus 7 divided by parenthesis x squared minus 49. Got to graph the original function. Got to graph the original function. One vertical asymptote, separate my graph in 2 parts. 2 vertical asymptotes, separate between 3 parts in the picture. Alright, so I'm gonna take a picture of this thing. So technically, the vertical asymptote you don't see, there's actually one right here at x equal to 7. Okay, at x equal to 7. That's my vertical asymptote. But if you really think about the restriction on the domain, this x actually cannot be positive 7, and this x cannot be negative 7. So the factor that I canceled out, what is that? Well, if you look on the table, if I will actually go to x equal to negative 7, it will still send an error. Okay, so as this line keep on going to negative 7, what's happening is there is actually a hole. Whatever the factor I canceled out, set equal to 0, it's actually referring to a hole in my graph. 1, 2, 3, 4, 5, 6, 7. There's actually a tiny little hole right here at 7. So that made my graph discontinuous at x equal to -7. It's actually a tiny little hole right there. Okay, so those are my restrictions on the domain: a vertical asymptote and a hole in my graph. All right. Another type of asymptote is called the horizontal asymptote, and this is something we need to remember when we're talking about how to find the horizontal asymptote, because there are 3 scenarios. Okay, so horizontal asymptote is just like a horizontal line, okay, that divides my function in different parts. Okay, so the first scenario is when the numerator and the denominator, and this is my fault, when the degree, sorry about that, when the degree of the numerator and the denominators have the same thing. When numerator and denominator have the same degrees. When the degree of the numerator and the denominators are the same, the leading coefficient is the horizontal asymptote. So my example here, the degree of my numerator is 2, degree of the denominator is also 2. So same degree, the leading coefficient will be the horizontal asymptote. So that will be 12 over 3. And 12 over 3 is 4. So horizontal asymptote is a horizontal line. So my equation for my horizontal asymptote is y equal to 4. Alright. When the degree of the numerator is less than the degree of the denominator, then the x-axis, which is also the same thing as y equal to 0. We mentioned this back when we talking about polynomial inequality. Okay, equal to 0 means what's on the x-axis. Alright, so when the degree of a numerator is less than the degree of the denominator, then the x-axis or y equal to 0 is the horizontal asymptote. So this example, degree of numerator is 1, bottom is 2. So y equal to 0 over the x-axis will be my horizontal asymptote. So let's go back up to the previous problem we just graphed. Degree of numerator is 1, degree of denominator is 2. So numerator is less than that. So that means the horizontal asymptote is actually the entire x-axis. Okay. Now the function can never cross over the vertical asymptote, but sometimes the graph can cross over the horizontal asymptote. Okay. Sometimes it can, sometimes it will not. And I will explain a little bit more when we begin to talk about the graphing of these rational function in a different objective. Alright, graph cannot cross over vertical asymptote, just cannot happen, but sometimes it may cross over the horizontal asymptote. When the degree of the numerator is bigger than the degree of the denominator, then there is no horizontal asymptote. Okay, this is 3, that's 2, so there's no horizontal asymptote. So what do you have instead? Well, to be more specific, something called the slant asymptote. The slant asymptote will occur when the degree of the numerator is 1 greater than the degree of the denominator. Just like this particular example. This particular example, degree of the numerator is 1 greater than the bottom. Then what you have here is a slant asymptote. Okay, so I brought this example over so I can show you how to find the slant asymptote. Okay, to find the slant asymptote, we will use the long division. So this degree of the numerator is 2, the bottom is 1, so this is 1 greater. Okay, so what we have is called a slant asymptote. No horizontal is called a slant asymptote. So I'm going to do long division for this problem. I know this particular example I can use synthetic, but I'm going to go with long division here real quick. Alright, 1x minus 3. There's no missing term. That's 1x squared plus 1x minus 6. Alright, true term on the outside, go to true term in the inside at a time. First quotient, go on top of the positive 1x. Take my first term on the outside, go into the first term in the inside one time. Then once I wrote down my quotient on top, begin to multiply the terms on the outside. 1 times 1 is 1. 1 times negative 3 is negative 3. Long division, we will subtract. 1 minus 1 cancels out. That's what I want. First term canceled out. 1 minus negative 3 is a 4. Bring down the next term. Negative 6 down and start my process over. 1 going to positive 4 times. 4 times 1 is 4. 4 times negative 3 is negative 12. Long division, I will subtract. First term cancels out. Negative 6 subtract negative 12 is positive 6. When I get done with the problem, I look back up to the top and see my first quotient 1 is lined up with the x column. So technically my answer is x plus 4 plus my remainder over the divisor. So what happened here with the remainder is, if x is approaching infinity, if this x is approaching infinity, that is going to be super large. A number divided by a super large number will actually becomes 0. So that's the reason why when we find slant asymptote, all we needed is the quotient on the top to be our answer. Okay, we don't need the remainder. So my answer just x plus 4. Alright, let's try this again real quick. Now this one has a lot of missing terms. I'm going to do this problem and I'm going to graph it for you, okay? 12x to the third. I'm missing quite a few terms. I'm missing 0x squared, 0x, and the constant term is 0. This is 3x squared plus 0x plus 1. Alright, 3 term on the outside, going to 3 term in the inside at a time. 3 going to 12 4 times. That's 12, 0, positive 4. Long division, we will subtract. First term cancels out. 0 minus 0 is 0. 0 minus 4 is negative 4. Alright, bring on the last term. Real quick, this is 3 going to 0, positive 0 times. And I can stop it here. I don't need my remainder. My first quotient on top is sitting at x column. So my actual answer is 4x. So this 4x is referring to a linear line that will actually divide my graph into different parts. Let me show you here on the graphing calculator what the slant asymptote does. 12x to the third divided by 3x squared plus 1. Okay. I'm gonna go to my window and make my things bigger. Negative 50 to 50, because there might be something on the outside of my picture I don't see. Nope, there's none. Alrighty. So what's happening here? Remember now, this is 4x plus 0. Picture looks very strange for a rational function because it appears to be a straight line, but it's not. There's a little curvature right here. Okay. So what's happening here is this is actually two parts to it. There's actually a straight line, y equal to 4x, actually separate my graph into different parts. Now let's go this way. It's a little bit tight right here. So one part stay on one side, the other part stay on the other side of my y equal to 4x. So graphically, that's what it's gonna look like. Okay, but you don't see it. It's really hard to see it on here, because if I say x equal to 0, y is 0, that's the origin. If I say x is 1, y is 4. If I say x is -1, y is -4. You know what I'm saying? So if I go to my table, go to 1 and -1, for the actual function, 1 and -1 is -3 and 3. But for this horizontal line, it's actually 4 and -4. So I graph it a little bit weird. I need to graph it out a little bit. My line is a little bit crooked. 4, so I'm staying on the outside, maybe more like this. I'm just kind of giving you an example. It's not very accurate. Okay. So it shouldn't turn this much, but I can't switch it over. Sorry about that. There we go. More something like this. Okay, the two line actually does not intersect. I just can't really get my line straight, square enough where it doesn't intersect. All right, thank you for watching.